developing next-generation research and technology, facilitating connections between AFRL industry and academia, unlocking innovation through a culture of collaboration. This is the AFRL Regional Network Midwest.
We are working on a semiconductor laser, and we're trying to take it from a technology readiness level 1 to 4. In particular, in this project, we're working on the semiconductor laser and we're trying to increase its brightness. Now, to increase the power in the semiconductor laser, the most straightforward thing is to just increase the active volume. The problem is you have more modes that come in, and so then you're essentially stealing your brightness. To do this, we're going to use what's known as a photonic crystal surface-emitting laser. These are devices which use a two-dimensional refractive index pattern, which basically creates an index profile which can engineer the modes of the cavity. And so what we want to do is come up with a structure which allows just one mode delays. This has been pursued for more than 20 years, and up till now, what people typically do in order to make these two-dimensional photonic crystals is they etch holes into a semiconductor, and then they epitaxially grow over that to seal off the holes. So this is potentially unreliable. So what we would like to do in this work is to replace those encapsulated voids with dielectric.
Now, normally we grow on perfectly crystalline, atomically smooth 3-5 wafer surfaces. So the challenge here lies in growing on top of patterned SiO2 photonic crystals. The SiO2 is amorphous, so it is critical to avoid deposition on those regions in order to prevent random polycrystalline growth. So the secret sauce lies in a process called selective growth, where the 3-5 material only deposits on the wafer surface and ultimately buries the low index photonic crystal in high index single crystal semiconductor material. This combination of patterning and epitaxial regrowth opens completely new ways to control optical modes in 3-5 lasers, and so we're excited to be part of this project.
I'm here in the semiconductor laser testing lab. One of the things we are very interested in is high brightness semiconductor laser sources at infrared wavelengths. The team at University of Illinois is proposing and working on a high brightness 1550 nanometer laser using indium phosphide and photonic crystal surface emitting lasers to reach these high brightnesses and high powers needed for applications such as LiDAR. And 1550 is good for eye safety, and it's also a telecommunications wavelength range. And the techniques they're using, we will be able to leverage for other programs for high brightness semiconductor laser sources.
So we accomplished several of our milestones in the first increment of this project. The first 2-month milestones that we achieved were the development of the electron beam lithography process for the thin SiO2, and also the development of the longitudinal mode simulations.
We were also able to achieve high fidelity dry etching of both indium phosphide and dielectric, as well as achieving selective overgrowth and lateral epitaxial overgrowth, both from indium phosphide and from a quaternary indium gallium arsenide phosphide, which to our knowledge is the first that's been achieved.
And in month 6, we were able to get done photo dumped edge pixel measurements, along with month 9 achievement of buried dielectric pixel, which are fabricated and characterized.
One of the growth-related achievements that we accomplished in the last segment was decreasing the roughness of the surface of our devices. While the photonic crystal itself is still contributing to roughness, you can see the inner parts of the squares in these images. Increasing the phosphorus to indium ratio significantly decreases the roughness outside of the photonic crystal, which allows us to maintain our selective growth regime while not suffering a roughness penalty, at least outside of the photonic crystal region.
We wanted to analyze if dry etching affected the surface roughness of the samples. So with one sample, we dry etched it, and another sample we did not, and there is no significant difference of the two in the surface roughness.
We were able to successfully bury these SiO2 triangles with the epitaxial lateral overgrowth. And these were for about a fill factor of 40%. And we see that the average index with such a high percentage of SiO2 is going to really, in this lower region, really push the mode away from the photonic crystal, which is detrimental. So to increase the mode overlap with the active region, we want to decrease the fill factor of the triangles. And so we found, compared to literature, we think we need to be at least above 7% overlap with the photonic crystal region. So we fabricated devices with 13% and also 10% fill factor SiO2. So in the second increment, we have increased the TRL level from 2 to 3 by demonstrating lasing in the undoped photopumped pixels. So we did decrease the fill factors to 13% and 10%. We demonstrated successful smooth overgrowth of the surface. This is the pattern region of the pixel, and this is the non-pattern region. We can see from the SEM view that the surfaces are very similar. And we found, scanning over several different lattice constants, we are able to see lasing emission with a narrow line width. And that emission wavelength scaled with the lattice constant, which is what we expect. And we were able to see this on-axis center beam in the far field profile that's projected onto a screen.
In the third increment, we will demonstrate lasing in doped photopumped pixels.